All right, this is the last topic we're going to look at in this class, and it's Taylor and Maclaurin series. So far we've looked at series representations of functions, but we've only looked at the functions that were really kind of easy to do. Things that had the form a over 1 minus r, and a few other things that were closely related, like arctan and natural log of 1 minus x. So the question is, can we find power series representations of other functions? And the answer is yes, we can find them for a lot of different functions. So let's build up how to do that. So first up, suppose that f of x is a function that can be represented as a series. For now, we're going to center the series at x equals 0, and we can write this function out as the series f of x equals coefficient 0 plus coefficient 1 times x, coefficient 2 times x squared, and so on. And this is true, or this equality holds whenever x is within the radius of convergence away from 0. And this is called the Maclaurin series for the function. The Maclaurin series is exactly equal to the function at all values where x converges. Now, the thing that makes this a series is the fact that it goes on forever. If we were to stop it and say here, and just look at these first 4 terms, that would be a polynomial. If we do that, that's called a Maclaurin Polynomial. And Maclaurin, I say Maclaurin, but it's a Maclaurin Polynomial. Maclaurin polynomials will approximate the function pretty well. So what I want to do is look at how to come up with these Maclaurin polynomials for given functions. We're going to see later that there's a big chart that tells us how to do it. But rather than just giving you the chart, let's look at how to do this. Okay, so let's start with the Maclaurin series for e to the x, because that's a nice, easy function to deal with. So I've got this written backward from up there, but let's let e to the x equal this series here. And what we're going to do is we're going to go in and solve for each one of those coefficients by plugging in 0 into the function, its derivative, and its second derivative, and so on. All right, so first up, let's look at this. If we take this one and we find f of 0, that's going to give us c sub 0, but then all the rest of these terms are going to just be 0. So over here on this side, we've got f of 0 equals 0. And from this side over here, we get it's equal to e to the 0. So e to the 0 is 1. So that gives me my first coefficient. C0 is 1. Okay. Now, if we take the derivative of this, we get this function down here. So we get, C0 goes away, we get C1 plus 2C2x, 3C3x squared, and so on. So now we'll plug 0 in again. F prime of 0 here is going to be C1. All the rest of these terms get zeroed out. And over here, this is equal to e to the 0. So again, we get C1 is equal to 1. All right, so our first two coefficients are 1. All right, now let's take the derivative of this, and we'll come up with this. I want to step through this a little bit here. Let's see, derivative of this is 0. Derivative of this is going to be 2c2. Derivative of this is going to be 6c3, but I'm going to keep that written out as 2 times 3c3 times x. This is going to give me 3 times 4x to the second power, and so on. So now let's take f double prime of 0. We get 2c0. All the rest of these terms just 0 away. And we get this is equal to, again, e to the 0, which is 1. So this time, that should be a C2, not a C0. We get C2 is equal to 1/2. All right, and we'll do this one more time. Take the derivative of this. This, of course, goes away. this becomes 2 times 3 C3. This becomes 2 times 3 times 4 times C4x. And then we get more terms over here. If you plug in f prime 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 of 0, you get 2 times 3 times C3 equals e to the 0, which is 1. So C3 is 1/6. And we can keep doing this as long as we want to. I've got one more, so let's do it. If we take the derivative again, we get the fourth derivative is this. If you plug in 0 for this, you get 2 times 3 times 4, that's 24. So you get C4 is 1 over 24. Now, you might notice what's going on. In general, the coefficient for this is for just for the Maclaurin series of this function. Well, before we look at that, we've got these different coefficients. So let's write out the Maclaurin polynomial. E to the x is equal to 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th plus dot dot dot. With the dot 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 on there, it's the series. If I take the dot 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 off, it's a polynomial. Let's take it off. All right, let's compare this to the graph. All right, so on Desmos here, I'm going to put in two things. I'm going to put in y equals e to the x, which looks like that. And then I'm going to put in this polynomial that we just found. Y equals 1 plus x plus 1/2 x squared plus 1/6 x to the 3rd plus 1 over 24 x to the 4th. All right, and if you look at that, this looks like a pretty good approximation, at least for a while. Right here in the middle, these two functions are right there on one another. So this is a good approximation. Of course, the red function is an exponential, and the blue function there is a 4th degree polynomial. And if I start taking these off, we get a 3rd degree polynomial, 2nd degree, 1st degree. And this is centered at 0, meaning the approximation is perfect at 0. Even if we just put the 0 degree polynomial in there, that is a perfect approximation, but only at 0. As we put more terms in, the approximation is going to get better and better. Let's put this in using sigma notation. The way you do that is you type in sum. N is going to go from 0 to, I'm just going to call this L up here. But what's our formula? We didn't work the formula out. Let's go back and look. In general, the coefficient of the Maclaurin series is this. Now, for e to the x, then all of these derivatives here, the notation here, remember, when you've got a superscripted n like that inside of parentheses, that means the nth derivative. So if f of x equals x, Cn is going to be this. The derivative, when you plug in 0 for e to the x, you're always going to get 1. So your coefficients are going to be 1 over n factorial. So let's put that into Desmos. what I've got here is on top, I've got x to the n. And on bottom, I've got n factorial. And I've got to add a slider for L. Let's let L go from 1 to, say, 20, step 1. So as L grows larger, this will become a better and better approximation. By the time we've got it up to 20 there, I mean, that's a 20-degree polynomial that's approximating e to the x. And, you know, it looks really good over here. It starts to break down. But if I just change this to something bigger, and this is probably going to make my computer choke. But if I put this in, notice the approximation gets good further back. And if I could put in an infinity up there at the top, this would be an approximation that, well, it wouldn't be an approximation anymore. If I could make it go to infinity, it would be exactly equal to it everywhere.